So I changed the title slide here when I heard a few people speak. I'm new to the Ember community. This is awesome. There's a real good knit here across Europe and the US. It's crazy. It's really cool. IETF is not the same place. We'll get into that in a little bit. I used to be a web developer. I was very comfortable sitting in my web developer space. I was there for a number of years doing a whole bunch of things in the PHP days and some JavaScript as well. I work for a mobile operator association. Mobile operators are members of the association. I do some work for them in IETF and in W3C. And throughout the last 4 years, I've been pushed further down the stack. And that's where we're going to be going now, into the deep depths of mostly the transport layer. If you guys don't know much about the OSI model, it looks mildly like this. You guys are looking at Ember stuff, which is built on web technologies. Web technologies run over HTTP, which was on the application layer. HTTP sits on TLS, which does most of the encryption for the web and some other technologies as well. That runs on top of the transport layer, which is mostly TCP. And I say mostly TCP, and it really is. Like 85% is TCP. Actually, maybe even more than that. And which runs over the Internet Protocol, which most people should understand. Before we talk about what I'm here to talk about today, which is some of the developments in protocols across the application and transport layers, we need to understand some fundamental limitations. Inside of mobile operator land, some of these things are very obvious, but we don't talk about them a lot here in the web community. So 300 million meters a second is, anyone? That's right, is the speed of light. The speed of light is a massive limitation to network engineering. And it's amazing how many people work in network engineering and completely forget it exists. So at 300 million meters a second, this is how far you can get in 1 millisecond. That is it, right? If your content is in San Francisco, you can get to the next state. You can't get any further than that. If your content is in San Francisco, in 10 milliseconds, you can probably make it to Chicago. If you're going at line of sight, which the internet doesn't work like that. This is important, and not for, again, for your community, but for my community, it's very important. 10 milliseconds of latency is the goals that people are trying to achieve in 5G. Now, people might not know much about operator networks apart from what you see on your phone. Every time there's a new generation in mobile devices, it usually means a brand new hardware rollout and a massive upgrade in latency, or like lower latencies and better bandwidth. 5G is going to be a little bit more complicated than that, but effectively that's what it is. 10 millisecond latency is the goals for content to be received on 5G, which is really interesting because technically physically that's not possible. And like I said, that is actually only one way. 10 milliseconds means you're supposed to make a request and for it to come back. So even that is not quite right. And the hop thing is a big issue. There's a few websites where you can go and have a look at hops around the internet, and also where pervasive monitoring happens. But this gives a good indication of that. So this isn't really great. We're over here right now, and our content can pretty much only get to there in 10 milliseconds. One of the key things you can do is obviously deploy CDNs. I had a discussion last night over dinner, and I'm afraid CDNs or any kind of edge computing is still a thing that you might have to do, mostly because you cannot get over the speed of light issue. Unfortunately, it's something that's not going away. Another thing which makes things a little bit more complicated is what we call access networks. The mobile operator network is an access network. You make a data request through the mobile operator network and then you go out into the internet. The mobile operator network is a completely different set of architecture to the main internet. On 3G, it may take you 500 milliseconds to even get a connection to the mobile operator network. In 4G, it could be less than 100 milliseconds. It could be faster, but less than 100 milliseconds sounds about right. In 5G, it will be a lot quicker, but that's what you're looking at right now. The other problem you have is the amount of data. Now, I've been desperately searching for flights for this summer's vacation, which I finally sorted out. So I've been visiting this site a lot recently. I did load this in a private browsing window to get this information in Google DevTools. This is the key bit down here. People at the back won't be able to read. A fresh request to this website meant there was 192 requests made and 2.9 megabytes of data transferred. This is not a lot by normal web standards. This is actually quite common now for there to be over 100 requests per new page load and somewhere between 800K to 2.5 megs of data. Some interesting things to note here is if you play around in DevTools, I'm sure all of you do, is the protocols. You can actually get some idea of the protocols being used. I was trying to do this morning at home and realized that I was making all HTTP1 requests, even on Google stuff. So I think somebody's doing something really bad at my ISP, and I'm going to have fun looking at that when I get home tonight, making some nice, interesting calls. So you've got these two major issues, right? You've got the speed and distance, which is all capped by the speed of light, and the amount of data that you have. Another issue that you have, sorry, lots of issues, is the round-trip time issue. And unfortunately, there's not a lot of things that you guys can do about this. This is largely up to the protocol developers. Round trips are evil, and round trips are mostly evil because of where the content is and the latencies associated with that. You can do everything on your app to make it performant and fast and render quickly and all those things. But if your content's really far away and the protocols are requiring you to do lots of round trips to get it, then you've got some huge problems. Let's talk about HTTP1 to understand why that's true. So in HTTP1, this is a stack, goes over IP. IP is what we call a point-to-point protocol. It hops between routers on the internet. Everything else is end-to-end. So there's an end-to-end HTTP connection. There's an end-to-end TCP connection. If you make a request in HTTP1, you have to wait for the response until another request gets sent. Now, this was OK when the web looked like this and you were making 3 requests for 2 images and a text file. But it's not so great now when you have the 192 requests and X megabytes of data. And it's even worse when you're doing this, when you're going all the way back to somewhere where, to get content and bring it back over. There are some things you guys can do. I'm sure you know about them already. Image spriting, stick all your images into one file. Inlining code. I'm not an expert on these things, so I'm sure you guys know about this stuff. And I know there's a whole other issue with inlining. We won't get into that in this talk. And then you could do this, which is great. Thank you, Martin, earlier. Service Worker is actually really good. It's really good for taking data off of the network. So mobile operators actually really like it. Get data off of the network, give users the same experience. Yeah, brilliant. Happy with that. One thing that the protocol developers and browser vendors, operating system vendors have been working on a long time is pipelining. This is something that they can do. You guys can't do, but they do that. So how I like to think about pipelining is if you are part of a number of people trying to get to a supermarket. So way back in the day, and this is the case still for a number of people, you would use a road to drive along to the supermarket. That road has one lane, so eventually you just make a queue and you're sending a load of data, or in these particular cars, to the supermarket. Pipelining is opening up more lanes, so you can allow more cars to travel. All of these roads are sharing the same bandwidth, and for the sake of argument, we are going to say that the cars cannot change lanes. So that doesn't happen, just imagine. So we've opened up all of these connections. Pipelining literally means opening more connections. Usually browsers will open up 6 TCP connections, and they'll all be competing for bandwidth, and they'll be trying to send packets through these connections. The problem is then you have massive overhead of TCP setting up all these connections. And this is the round-trip time to usually set up some kind of TCP connection with an HTTP over TLS. So you have the TCP setup, which will take 1 round trip. If you're lucky, it may take more. And then you have the TLS setup, which again will take 2 round trips, but if you're not lucky, it might take 3, before you can even send a response. And this has to happen 6 times for every single one of these TCP connections. So they wanted to work on a new protocol at the IETF to solve some of these issues that are being experienced in the modern web and on other applications as well. But it didn't start in the IETF, it actually started at Google. Google originally worked on a protocol called SPDY. One of the gifts of SPDY is taking the idea of pipelining and doing this. Now, I know we have some people from out of town. Ocado is a delivery service, a supermarket delivery service. So rather than all these cars going to a supermarket, we order online and the van delivers a number of these, the items that we've delivered to our home. And that's effectively what multiplexing is. And that's what SPDY started. So it said, instead of opening all these connections, let's have one TCP connection. Let's take all of these requests, multiplex them over that one connection. Then they can use the bandwidth properly, and you don't need to wait for a request and response before sending another request. SPDY did a few other things. One of its other great gifts was header compression. Headers are kind of crazy in HTTP. If you've done any HTTP debugging, you'll see that headers are largely text-based. They used to be text-based. And that makes debugging very, very nice because you just look into the HTTP headers and find out what's going on. But they take up a lot of space. And because of that, it starts to really clog up the network and make things very, very slow. SPDY also used TLS. Google said that they wanted to use encryption with SPDY to make it work over the networks because they found some middle boxes, things like firewalls and NATs were blocking a SPDY on the network, so they used encryption to allow it to sort of tunnel over the network. There's some issues with that. If you want to go ahead and look at SPDY headers and how they work, and you can inspect with Chrome DevTools, this is actually for QUIC, but it's the same type of thing. So in August of 2014, these browsers had implemented SPDY. The ones on the left are owned by Google, but there was actually some other browsers who had implemented that. And at that point, it seemed like it was the right time to bring it to the IETF. And I had a few people mentioning RFCs today, which I thought was really weird. I was like, I didn't know Ember had RFCs. IETF also uses RFCs for standards. So if a protocol becomes a standard, it has an RFC and it has an RFC number. IETF is the Internet Engineering Task Force. It does all the protocol standardization. W3C does all the API work, web API stuff, but it's IETF we're really focusing on today. So they started working on HTTP2. One of the key messages about HTTP2 was to maintain the HTTP semantics, but change how it was transported. There's going to be an underlying current in working on these protocols about not breaking the web and not breaking the internet. And one of the reasons for that is if you've done a lot of work in IETF, you'll see that protocols which aren't successful, so they get made into being standardization, but they don't get deployed and they don't get used, is because they don't really fit today's internet and they can't be implemented or used properly. So of course, the key thing that HTTP2 did was to learn from SPDY, and it did use SPDY as a base. So it took the 6 TCP connections thing, and then it multiplexed them. It said full multiplexing. So it meant that you could do this. You could send multiple requests. You didn't need to wait for a response. Response would come back at one point, and then you'd handled it through multiplexing. It did all the other things as SPDY. It had a server push. There was some priorities in there as well. I think that's still being worked on. Now, but the encryption thing was actually quite interesting. The chair of the HTTP group at IETF wrote this blog post, and after a lot of deliberation at the time, they decided not to have encryption as default for HTTP2. And it seems weird to think of now because the next protocol that we're going to talk about does have that. But at that time, it seemed like it was going to break too many parts of the web and the internet to have encryption by default. So that was the decision that was made within the group. In actuality, the browser vendors who implemented it only really implemented HTTP2, the encrypted version. So you'll find that lots of browsers will allow you to use HTTP2 if your site is encrypted, and if it's not, you fall back to HTTP1, even if you have HTTP2 enabled. That was sort of an undercurrent thing that went through the IETF, but it was an effort to promote this let's encrypt everything for a number of reasons that I'm happy to discuss over beer. So let's look at some stats. This I think is not that old. I think maybe a couple of months old. So 35% of requests from Firefox, this is stuff that's come out of Firefox, with 35% of their requests was HTTP2, 70% of their HTTPS connections, 13% of the top 1 million sites, 29% of the top is 1,000 sites. The message from one of the HTTP2 standardization experts was, if you implement HTTP2 on your site with encryption, 90% of the users that come to your website will be experiencing HTTP2. But there was some big blog posts when HTTP2 was standardized, and people started doing some heavy research into this about the downfalls of HTTP2. A number of people said that HTTP2 was great for very, very good connections and very poor for very bad ones. So this happens on the mobile network a lot. We don't measure, often mobile operators don't like to measure performance of mobile networks, because if you're very, very close to a base station, your connection's very strong. You move far away from the base station, suddenly you start to lose packets. And this is what we were experiencing with some HTTP2 connections. At a 2% packet loss, HTTP1 was better than HTTP2. For very, very poor connections, HTTP1 was performing better than HTTP2. Another issue that people were experiencing, and this was a big one that SPDY tried to get over, but it couldn't really get into HTTP2, is the idea of head-of-line blocking. So head-of-line blocking is a weird phenomenon, mostly, and we're going to talk about it on the transport layer particularly, where on a TCP connection, TCP will send packets. It will send packets in order, and it will expect to receive them in order. If it doesn't receive them in order, it will expect it to be retransmitted. So it can only take packets in order. If a packet gets lost, then the other packets behind it have to queue until that packet is retransmitted and received. Because of that, you get these blockages happening in the network. HTTP2 guys tried to solve this, but by using TCP, it wasn't going to be possible to overcome this issue, so it still exists, even with multiplexing. Oh, I explained all of those things, right, in these nice slides. So the idea came to start working on a different protocol. And again, this protocol was being worked on at Google, and its name is QUIC. So we're going to go through some details of QUIC. Again, the idea was to maintain HTTP semantics, but change how it was transported. So it's exactly the same thing. Don't break the internet. Don't go crazy. Let's see how we can be clever about this. So like I said, head-of-line blocking is mostly a TCP issue. So how do we solve it? We get rid of TCP. Instead of using TCP, we use UDP on the transport layer. Now, if you do any sort of transport inspection, you run up Wireshark and see how much TCP and UDP and other transport protocols you're using, you will see that it's mostly TCP. You'll see some UDP as well, and you'll see very little anything else. And the reason for that is something that we're going to discuss right now. John Iyengar, the guy who is one of the QUIC editors from Google, said this. He said, we want QUIC to work on today's internet. If you do any work in the IETF on transport layer and making inventive transport protocols, you'll find this is a very common thing that you have to deal with, ossification. I hate this word. I hate it so much. One of my big bugbears is people using incredibly complicated words within standards bodies when you have a very global audience and everybody gets very confused about what very long words mean. I'm going to explain it. So ossification is when bones form, when they get sturdy. I don't know anything about medical science. I just looked this up. And this applies actually to the transport layer. Because of things in the network such as middle boxes, and we're talking mostly about NATs and firewalls, DPI boxes, transport optimizers, any kinds of blocks or filters in the network, especially in enterprise cases as well. Middle boxes tend to block everything that is not TCP and UDP sometimes. Some of them will block UDP as well. So because of this, your only choice if you want to make a protocol for today's internet on the transport layer is to use TCP or UDP. Now, UDP is a different protocol to TCP. TCP does in-order delivery, and it looks after its traffic. If you send traffic, TCP will make sure that it's delivered. UDP doesn't care. It's lossy. It's just send stuff. And that's why it's very good for streaming. So QUIC has to be a bigger protocol than some of the things before it. So you'll see here we've got application layer over QUIC, over UDP, over IP. Originally we had HTTP2 over TLS. TLS was a separate protocol over TCP over IP. QUIC has a little bit more stuff to do. It does its own congestion control, which is again controlled by packet numbers, but it does something a little bit funky with those. And initially, when it was developed at Google, they had their own crypto that they developed, and they baked it into the protocol. So it's part of the protocol, how the protocol flows. This was a little dodgy, just a little, because if you have a look at net internals again, or in the developer toolkit, you'll see here that you're using HTTP2 on the protocol list. You're HTTP2 with QUIC. Up in the URL bar, you've got HTTPS. Now, HTTPS, as you understand it, is a standardized protocol. It's HTTP over TLS. If you're using Google Crypto, and I think you are if you're using QUIC 35, then you're using a non-standardized crypto. Now, luckily, most of us trust Google, and the crypto that they make is great, but it's not a standardized crypto. So a few people had some issues with that. Again, Google brought this to the IETF to work on it collaboratively, which is great. And one of the major standardization efforts was to, first of all, agree on the crypto. They swapped it out for Google Crypto and inserted TLS 1.3 there. The major benefit of TLS 1.3 is the 0 round trip time that you can get when you go to a website you have visited before, or go to an Insta entity that you visited before. On TLS 1.2, it's still 2 round trips, so that's the major benefit of TLS 1.3. IETF also wanted other protocols to go over QUIC, not just HTTP. So they're standardizing it in a different way to how Google developed it, but again, using QUIC as a base. The way that they do this is mostly using what we call streams. So streams allow HTTP2 and they allow QUIC to multiplex. So it gets a little complicated, but it's all set up to work. HTTP over QUIC will take a requests and responses and put those into streams. The one HTTP connection will put all those streams together and send them down to QUIC, which in turn takes multiple of these HTTP streams and then filters them down into QUIC connections, and then these flow, multiplexing over UDP. So because you have all these multiple streams running over one UDP connection, you can make full multiplexing throughout the whole protocol stack. Now that means you can get rid of head-of-line blocking, because if one packet drops, it doesn't delay anything else because of the nature of streams. This means that QUIC has one connection set up, which is great, one loss recovery context, one congestion control context, and you can have priorities in there if you want, or I don't think priorities work. Again, happy to discuss that over a beer. Remember again, that our round trip times are evil. So what we really want to know about is how does QUIC help our round trip time issue? Well, because you're only setting up one QUIC connection, and because of the nature of streams, we only have to do this connection bit once. And this is some of the key stuff. If you visited a website before, you can do 0 round trip times with QUIC. You send setup data and data in the same push. You have to have visited it before because you needed to have exchanged crypto keys. If you haven't exchanged crypto keys previously, it's 1 round trip. If you need to do a version negotiation, which you should have to do relatively rarely, it will be 2. If you want to see this in action, the best place to see it is in any Google to Google entity. So Google Chrome to a Google service, mostly YouTube. YouTube's a really good way to test out all your QUIC streams. It has been easy for Google to do a lot of this work because they own clients and because they own massive server backends and huge online entities such as YouTube. If you want to inspect it, Chrome //net-internal/ #QUIC is a good way to go and have a look at all of your streams. All of your sessions, you can get some pretty good detail by going into them. QUIC sessions are encrypted though, so it's unlikely you'll be able to see payloads. So how much has this impacted the internet as we know it today? By estimates by Sam Vine, which are a testing organization, they do a lot of work on internet testing, about 7% of the internet traffic today is running QUIC. But that's crazy. It's not even a standardized protocol. This is mostly to do with the fact that it is Google to Google, and that's why it's so high. 35% of Google's egress traffic is QUIC, and I believe that's growing. I have no actual sort of any more statistics about it because we're still trying to find out stuff ourselves. We've got a bit of an issue with how the mobile operator network is going to act with QUIC, mostly because the mobile operator network has its own retransmission cases and own congestion control, and that won't work with QUIC because of how much QUIC hides a lot of its data, which is good for so many reasons, again, which I'll discuss over a bit. But I've run out of time today, so I wanted to do just a small recap of some of the stuff that I've gone through, because like very many of my talks, we go through so many things. We talked about round trip times. We talked about the physics and the limitations that you have when you're dealing with round trips going around the world. We talked about how much data is flowing over the internet now for websites and how that impacts the site load. We talked about SPDY, HTTP2, and QUIC, so all of the history that's gone on to do with application layer protocols and how that's moving towards affecting transport layer protocols as well. Header compression, multiplexing, and streams, all of these new techniques are helping us to get a faster internet and a faster web. By the nature of abstraction, web developers don't need to worry about these things, but it is always great to understand how they work. With QUIC, head-of-line blocking has gone, which is a massive innovation for the internet. And we need to make sure if you do ever get into internet protocol work, which is fun, I promise, one of the greatest things that you could do is make protocols for today's internet. If you want protocols to be deployed, they have to work for the internet today. So I have to give one message about all of this work from the IETF working group. And this work on QUIC is not going to be HTTP3. It won't be called that. And it won't be called TCP2 either. That is definitely not going to happen. If you meet anybody from the IETF working group, depending on how mischievous you're feeling, just say, oh, how TCP2 going? Yeah, that. It is just going to be QUIC. It's on GitHub if you want to have a look at this current spec. And with that, I'll say thank you very much, and thank you to these people for their work on these great protocols.